Welcome back, class. So last time we talked about percent composition, right? Which was about taking the formula and breaking it down into the different elements and how much of that element was contributing to the compound. Well, the question is, can we go the opposite way, right? Can we take information about the percent composition or about the composition of the compound and get back to the formula? Now, the answer is sort of, right? What we can do is, if we know the percent composition or have some other information that allows us to know the breakdown, we can get back to a formula, but we can only get back to the empirical formula, right? So now remember, earlier in the chapter, we defined the empirical formula as the simplest whole number ratio of the atoms in a compound. Now, of course, this could also be the simplest whole number ratio of moles of elements, right? So, if we're looking at a compound, right, like CO2, we could say that CO2 contains one atom of carbon and two atoms of oxygen, right, if we had an individual molecule. But since we're going to tend to deal with moles of compounds, we can also say that 1 mole of this compound, right, would be made up of 1 mole of carbon atoms and 2 moles of oxygen atoms. Now, the other key things to understand is these are ratios when we have a formula here, right? They're ratios of atoms or moles of atoms, right? They are not, I repeat, not a ratio of masses, right? So we have to understand that they're telling me the makeup in terms of how many atoms of each element or how many moles of atoms of each element, not masses. So, but if we do know the breakdown, so for example, if we know the mass percent composition of this compound is 60% carbon, 4.48% hydrogen, 35.53% oxygen, right? So what would be a percent composition? I can get back to a formula, but it's going to be the simplest formula, right? Or what we call the empirical formula. Okay, so let's set out how we do that. Now, we also stated last time that, remember, anytime we have percentages, right, they're based on 100. Right? So if I have 60% carbon, what that tells me is I have 60 grams of carbon in any 100-gram sample. And so if I just choose a 100-gram sample and break it down, then I can convert these percentages directly into grams. So of that 100-gram sample, 60 grams are going to come from carbon, 4.48 grams are going to come from hydrogen, and 35.53 grams are going to come from oxygen. Now, you not notice real quick that these percentages don't add up to exactly 100, right? I think they add up to 100.01, and that's not all that uncommon because of rounding errors and etc. So, but now we have our makeup of grams. So remember that the compound that we're dealing with here is going to have the formula of CXHYOZ, let's say. So it's going to have some number of carbon atoms, some number of hydrogen, some number of oxygen atoms. So we're going to have this ratio of atoms, or more importantly, moles of atoms here. So what we need to do is we need to take grams, because this is not a ratio of masses, and we need to convert them into moles. So the first thing we're going to do is, once we have our masses, we're going to take those masses and convert them into grams of the elements. So we're just going to start this, and we'll do carbon here first. So we got 60.0 grams of carbon. And we have 1 mole of carbon, 12.01 grams of carbon. So we're going to use our molar masses to go from moles to grams. And so you're going to get 4.996 moles of carbon. We're going to go on and do hydrogen, so 4.48 grams of hydrogen, 1 mole of hydrogen, it's about 1.01 grams. So we do that, we get 4.436 moles of hydrogen. And we go do the oxygen, 35.53 grams of oxygen times 1 mole of oxygen, 16.00 grams of oxygen. And if I do that out, I get 2.221 moles of oxygen. Now, again, you might start to now recognize as we get more and more to this how often we're going to use some of these calculations, right? Converting grams into moles and using these molar masses, right? And so, but, we're always just following our units, right? So we got the grams are going to cancel, so we're going to end up with moles of my individual elements. Okay, so now we have a ratio of moles. So I could rewrite this formula now as carbon 4.996, hydrogen 4.436, and oxygen 2.221. But this is not very useful, right? Because chemical formulas have to be whole numbers, right? We need these to be a whole number ratio. So now we have a ratio here. It's just not a whole number ratio. So how do we turn it into a whole number ratio? Well, there's 2 basic steps that we can do. The first thing that we always do is we set the smallest one equal to 1. So in other words, we divide all of these by the smallest number of moles. So in this case, we're going to divide everything by 2.221. And what that does is it automatically sets this to 1, and we divide both of these by 2.221, and here we get 1.997 moles of hydrogen, and here we get 2.249 moles of carbon. So, do we have a whole number ratio now? Well, we're not bad, right? So this is a whole number. This is close to a whole number, right? We could round that to a whole number too. Now, unfortunately, this one is not a whole number, right? It ends in 0.249 or close to 0.25. So this is where this little table comes into play over here. So if we look at our fractional parts here, and a lot of times this fractional part is such that we can multiply it by some small whole number to convert it to a whole number. So like if we have something that ends in 0.25 here, we can multiply by 4 and turn it into a whole number. So other examples might be if we had something that was ending near 0.5, we could multiply it by 2. Something ending in 0.33 or 0.66, right? We can multiply by 3 to turn it into a whole number. 0.75, multiply by 4, right? So we look for this, and so we got very close to 0.25. So we can turn this into a whole number by multiplying by 3. So if we multiply by 4. So if we multiply this by 4, what does this become? It becomes 8.996, or approximately 9. Now, of course, I can't just do it here, right? I have to do it to everything, otherwise I don't maintain my ratio. So whatever we do to one thing, we have to do it to everything. We divided them all by the smallest. We have to multiply them all by 4 here. So I'm going to times this one by 4, and I'm going to get 7.99, or approximately 8. And of course I multiply this by 4, and I get 4. So now I have what would be a whole number ratio. So I have 9 carbons, I have 8 hydrogens, and I have 4 oxygens. And this becomes my empirical formula. Now, you might ask about the molecular formula. Now, with this particular problem, we have no way to get to the molecular formula. Now, it could turn out that the empirical formula and the molecular formula are the same, but we don't have enough information to get to the molecular formula. We will look at that at the end of this lecture here, and we'll talk about how we go from empirical to molecular formula. We need a little bit more data. But before we jump into there, let's do one more example of an empirical formula calculation. Okay. In our second example, we're starting off with a little bit different data. So if we look at this problem, it says we combusted, or we had the combustion of 0.8233 grams, a sample of a compound that contained only carbon, hydrogen, and oxygen. Produced the following: 2.445 grams of carbon dioxide and 0.6003 grams of water. Now, this is a specific technique called, represents an example of a technique called combustion analysis. And it relies on the fact that because when we do a combustion reaction, so when we do an example where we have a compound that contains carbon, hydrogen, and oxygen, and we burn it in the presence of oxygen, we only get carbon dioxide and water, right? Those are the only two products. And what we can say is that all of the carbon ends up in the CO2, and all of the hydrogen ends up in the water. Now, the oxygen gets spread out, and so we're going to have to do a little extra calculation to figure out the amount of oxygen, but we'll talk about that when we get to that point in the calculation. So let's get started. So the first thing we need to figure out here is we have grams of carbon dioxide. Ultimately, what I need to figure out, just like I did in the last one, is I need to get this to moles of carbon. And I need to get this to moles of hydrogen, right? So I can figure out what these are. Well, how can I do that? Well, we can't do it directly. So in the last example, since we knew the mass of each individual atom, we could just go directly to the moles, right? Using the molar mass. So here we have to do a slightly longer process. I just have to do an extra step here. So if we start with my 2.445 grams of CO2, I can convert that into moles of CO2 by calculating the molar mass of CO2, and we did this on a previous slide, so I'm just going to show it here. So 1 mole equals 44.01 grams of carbon dioxide. So at this point, we have grams of carbon dioxide, or we have moles of carbon dioxide. But we want moles of carbon. Well, if I look at the formula, within carbon dioxide, I see that there is 1 mole of carbon per every mole of CO2. So if I have 1 mole of carbon atoms per every 1 mole of CO2 molecules, now I have a way to convert into moles of carbon. So if I go ahead and do this math, I end up with 0.05556 moles of carbon. Now, I haven't mentioned this yet, but I guess I kind of took it as a given, but I will remind you at this point that it is a good idea to either, as you're listening to these or pausing them, that you're doing the calculations along with me here so that you're making sure that you're getting the same answers and getting the correct answers as you go through this. Okay, so now we have moles of carbon. Now let's do the same thing with the water to get to moles of hydrogen. So I have 0.6003 grams of water. I'm going to do the same kind of idea. I'm going to first convert it into moles of water. And water is going to have a molar mass of 18.02 grams. And if I look at my water, I have 2 moles of hydrogen for every 1 mole of water. So if I follow my dimensional analysis, follow my units, my grams of water cancel, my moles of water cancel, and I'm going to be left with moles of hydrogen. So if I do this, I get 0.06662 moles of hydrogen. So now, at this point, I kind of know what these are, right? I know I could rewrite this as carbon 0.05556, hydrogen 0.0662, oxygen, right? I don't know what the oxygen is. So I'm setting up this ratio. Now, how can I get to the oxygen? Well, we have to go back to our mass here. Right? So I know that this 0.8233 grams of my compound, of my CXHYOZ, right, is going to equal grams of carbon plus grams of oxygen plus grams of hydrogen. Here, let's write this. Sorry, let me go back and write this in the right, better order here. So grams of carbon plus grams of hydrogen plus grams of oxygen. Now, I have the ability to know what this one is and what this one is. So now that I know moles of carbon, right, I'm going to hold on to this number. I'm going to maybe use it later. But I'm going to convert this now into grams of carbon by using, again, the molar mass of carbon. So I know that there are 12.01 grams of carbon per 1 mole of carbon. And so if I do that, I get 0.6673 grams of carbon. So I'm going to put that down here, 0.6673 grams. Now my grams of hydrogen, I'm going to use my 1.01 grams of hydrogen, my molar mass, times 1 mole of hydrogen. Oops. And my units, of course, are going to cancel here, just like they canceled here. And I end up with 0.0673 grams of hydrogen. So if I put my grams of hydrogen down here, I have 0.0673 grams. So now I have the total mass, and I have the two parts, and I'm just missing the grams of oxygen. So now, this is pretty simple math, right? I just need to subtract these from here to see how much mass of oxygen I have to have. So I'm going to take my 0.8233 grams minus, if I add these two up, I get 0.7346 grams. 0.7346. And if I do that, this is going to equal grams of oxygen, and that equals 0.0887 grams of oxygen. So now I know how much oxygen I have, so now I can just jump right up here and have 0.0887 grams of oxygen, and I can get my moles of oxygen. So I have grams, moles, and 1 mole of oxygen, 16.00 grams of oxygen. And going to get me 0.00554 grams, moles of oxygen. So now I have the third part, right? Now, not quite done yet, because again, now I could fill this part in, so I have these, but just like I did with my empirical formula, I have to go through that process of dividing them each by the smallest one. So I'm going to go through and divide each of these by the smallest one, which would be 0.00554, and here I'm going to get 1 mole of oxygen. I'm going to divide this by 0.00554, and this by 0.00554, and you can see what those get us. So if I take this down, let me just kind of make a little divider here. So I take 0.05556 moles of carbon divided by 0.00554, I get 10.03 moles of carbon. And if I do my hydrogen here, I get 0.06662 moles of hydrogen divided by 0.00554. I get 12.03 moles of hydrogen. So now I have my moles, right? I have 10.03 or 10 moles of carbon. I have 12.03 or 12 moles of hydrogen. And I have 1 mole of oxygen, right? So all of these are whole numbers, so I don't need to multiply by anything. And I just need to then, my formula becomes C10H12O1. That becomes my empirical formula, C10H12O1. Now, I mentioned earlier that the process is a little simpler if you don't have oxygen, right? If you just have carbon and hydrogen. And essentially what that would mean is that you would not have to do, you wouldn't have to do any of this part here, right? Where you go back and calculate it, right? We could start directly from, once we had the moles of carbon and the moles of hydrogen, then we could go directly and divide by the smallest one, etc. Now, if you want to see an example like that, I would encourage you to, if you want an example with only carbon and hydrogen, see problem 3.20 in the book. And that'll give you one where you only have carbon and hydrogen. All right, so 2 different ways that we can establish an empirical formula based on the kind of data we start with, whether it's percent composition data or combustion analysis data. Now, last thing I want to do here is talk a little bit about how we get from the empirical formula to the molecular formula, or when that's possible. Now, the only way we can do that is if we know the molar mass, right? So, if all we know is the data that we've had before, we can get to the empirical. But the molecular formula, right, is always a multiple of the empirical formula. So remember, the empirical formula is just the simplest ratio. So the actual molecular formula is either going to be the same, or it's going to be twice that, or 3 times, or 4 times, etc. So it's always going to be a whole number multiple. The key is to figure out what that whole number is, and that's where n comes in. So n is that whole number multiple. So let's just say we're given this information and we have a compound that's let's do a different color here. Its empirical formula equals C2H3 and has a molar mass of 81.14 grams per mole. So the key is, now I know the molar mass. So now I have the ability to figure out n and to get to the empirical, to get to the molecular formula. So I need the molar mass, that's going to go on top. But I need the empirical formula molar mass too. So in other words, I need to know what the molar mass of this empirical formula is. So here I have 2 times 12.01 plus 3 times 1.01 equals 27.05 grams per mole is my empirical formula mass. So now I have my 2 key numbers, my molar mass, my empirical mass, and so I can calculate N. So N equals 81.14 grams per mole divided by 27.05 grams per mole. This equals 2.999, or approximately 3, right? So that's my N value, my multiplier. So that means the molecular formula equals the empirical formula C2H3 times 3, or C 3 times 2 is 6, H 3 times 3 is 9, so C6H9 would be my molecular formula. So in this case, it's 3 times what the empirical formula is. All right, so that wraps up what I want to talk about: molecular formulas, empirical formula. And the last topic that I want to talk about in this chapter, which I'll do in the next little segment, is just to do some very basic naming of a kind of compound that we haven't really talked about, and we won't really talk about much in this class, and that is organic or simple organic compounds, which if you move on in chemistry, you can spend a whole course talking about just these types of compounds. But we're just going to learn a very simple naming so that when they come up in examples and so forth, we kind of have an idea of what they're talking about.